Hi, good evening. Okay, even the Roman has showed that, as I promised, that I'm gonna go ahead and record this session and upload to the our course homework on the home page in that way that you can not gonna miss anything. Okay, so let's see that I have already shared the screen. I think I'm recording too. So let's go ahead and have a look at it. This our the quiz. Okay, first quiz, and see that. Uh, what we can get from this one. We can go through this one. Look at this one. The data from the NBA player 2011 includes data from the 2010-11 regular season for the 116 NBA basketball players. The head, select this. Not all that, some of the variables being selected, and there are 6 entries being displayed. Okay. So age, game starts, my minutes, minutes per game, FG made, goals made, field goal percentage, 3-point field goal made, 3-point field goal percentage, free throw made, free throw percentage, number of assists, okay, number of personal fouls, number of points recorded, okay. Hey Benjamin, good evening. I just started, okay. I just started. You didn't miss anything. That, as I promised even last time, that assuming if no one gonna that show up, that I'm gonna go ahead and record this one, then upload to the system. But since you are over here, very good. Okay. So what we are trying to do, that the quiz, the first quiz. Let's go through first quiz. See? Can you see this one? I think. Let's see. Oh no. Okay, good. You can see, no, the screen. Can you? Yeah. Okay, good. Yeah. Thank you. Yeah. So then these are the that these are the all the variables. Some variables being selected from this particular data. Okay, they selected NBA player 2000 from that one. That's the name of the data set. NBA player 2. You're gonna go to this one, and these are the variables, attributes. Don't worry about that. Yeah. So yeah, thank you. And then we finish. Whether you gonna leave or not, I'm gonna that the pretty much go through everything, and then we can record everything and upload in that. You're not gonna miss anything. Okay. Thanks. Okay. Thank you. Thank you very much. Yeah. So let's look at this one. Why do some players get more playing time and some players see less game time? See the game time. See minutes. Means game time. See minutes they played. So minutes they played, some players playing less game time. Some people play more playing time. Just look at the histogram of number of minutes played to start exploring this variation. What does the orange curve drawn on this histogram represent? It's been the histogram, but it's been, see, they have overlaid a smooth curve, normal smooth curve, see, on top of that one. This represents what? This represent population from which the data were drawn randomly. No, this is not the population. No, this is not the population from which that data has been taken out. No, we have this simply that overlay like a small smooth curved scheme in the top of that one, top of the sample histogram. Normally we're gonna call this one sample histogram because it's based on sample. If it is based on sample, we're gonna say sample histogram. And if it is based on population, we're going to call that one population histogram. If it is based on that average of the minutes, if you keep doing this one for a long time and then get the average, and then average has been repeated, then we're going to call sampling distribution. There are 3 types of distribution. We're going to talk about that one in next class. Okay. Next week. mainly. Okay. So here, this is a sample histogram. It doesn't represent any population. This represents a normal distribution, yes, normal distribution that was fit to the mean and standard deviation of this data. Yes, this has been fitted. You can remember how we're going to get this one. Okay? You can remember how we get this one by doing what? To get the histogram, you use the GF histogram, histogram, and then tilde, this one, means, comma, data. You can write like that. Okay? You can remember that in this one. You know, remember that one, first one, GF histogram. Okay. You can get that one by, if you go to the means, and the data is nothing but NBA players, no? You can remember. See? NBA players. See? NBA players 2011. NBA players 2011. And we're gonna connect to this one. Connect. This one. Right. Percentage greater than this one. And then GF what? You know, remember dist. No, GF dist. You use the GF dist for that one. And GF dist to get the smooth curve. How do you get the smooth curve? By doing what? This the GF dist. Then you can say normal distribution. See, norm, comma. What do you need? If you need any color, let's say that they have a color red or something. Color red, if you want red, comma. What else you're supposed to give? You're supposed to give the parameter. Params. Params means parameter means params. You can list. What are you gonna give? List. You give the mean. What's the mean? You go to how do you find the mean? You can find two ways. Okay, I'm gonna say this one. NB. No, I'm gonna call this one. I would say, what's the name of the variable? I'm gonna say the name of the variable. Name of the variable is means, no? Minutes. Okay, so I would say means stats, and go to mean stat, and from that one I'm gonna pick the mean. Then I'm gonna go to mean stat, and then I'm gonna put the standard deviation, close it. See, and close it. See? List being closed, and then I close again. I have a two right where you have to get this one where means stats you have to build up. That's nothing but favorite stats. I'm gonna go to the favorite stat now of what means data plus NBA players 2000 level. You get that stat one, you build this one, and from that one, you go ahead and read the mean and standard deviation from that particular sample. That sample, you can get to this one, see, this histogram, whatever the histogram we have here. Okay, I haven't drawn to the scale, okay. This is means, this count mean frequency, see? And we get the smooth curves in the same, like that. Is the normal approximated curve. And it is center. See, center is nothing but you go to min stats and min stat and mean. How about the spread? The spread. See, spread is nothing but you go to min stat. What stats mean? So we can work with the, you can take that out, and this one I'm going to call at this level sample histogram, and the same as sample distribution. You can call the sample distribution. Sample distribution. Like that. So in that sense, the answer should be mainly that this represents the normal distribution. That's what fit to the mean and the standard deviation of this data. That's B. Okay. One student suggests that the player who make a lot of free throws, FT made, are better and they would see more game time. Another student argues that making free throws doesn't make you a better player. Having a higher free throw percentage, FTPCT, is the sign of better player, and suggested that would explain the variation in minutes played means. Which of these plots would depict the relationship between means and one of these explanatory variables? Explanatory variable. Which of these plots would depict the relationship between the minutes and one of these explanatory variables? See? So the one student said player who make a lot of free throws, FT made, are better and they would see more game time. See? Game time means, okay? That's the Y variable. FT made is an X variable or explanatory variable. This one is a response variable. Then somebody argued and another student argued that making a free throw doesn't make you a better player. Having a higher free throw percentage is the sign of better player. He's suggesting this one would be the best attribute to explain the variation in minutes. Which of these plot would depict the relationship between means and one of these explanatory, one of them? Box plot, it is GF box plot, scatter plot, it is GF point, faceted histogram, all the above. You know that this one, minutes, FT made, or FT percentage, they both are quantitative. Minutes, quantitative to quantitative, quantitative versus quantitative. Then see, you can say, I'm going to get the minutes. Minutes would be my that major thing, okay? At the primary stage. See? So you're going to put the minutes here. See, Y would be means. X would be, sorry, FT. This would be, it would be FT made. Or X would be FT percentage, FT PCT. PCT, see? Free throw made and free throw percentage. Okay. Okay. So here, if that's the way that how you're going to find that one, what's the best way? This is quantitative. See, I'm trying to say quant. This is also quantitative. This is also quantitative. It's quantitative was quantitative. You definitely have what? Scatter plot. How do you get the scatter plot? By GEF point in R. In R, you get that GEF point. So you get the scatter plot. So if that's the case, what would be the plots? Scatter plots. Okay, not all of them. Not the box plot. Box plot that you can utilize for for the quantitative versus what? Categorical. Quantitative versus quantitative. Faceted histogram, quantitative versus categorical. See, this one, quantitative versus categorical. You can use the box plot to do the comparison and contrast. Then that's should be what? Quantitative versus categorical. Quantitative versus categorical. Box plot. Gender, female, male. Here, female, male. You can check it like that. Okay. We made this plot to explore the idea that free throw percentage FTPCT would predict how many minutes player gets to play. See, now they utilize this one FTPCT. If we fit an empty model of to this data, how would we depict it on this plot? You for sure you know that how that should be. Definitely you know that. See, minutes versus FTPCT. Minutes versus FTPCT. Here your Y is minutes and this is X. So you have a scatter plot. See? You have a scatter plot. But you need the empty model. See, empty model is nothing but this is your X bar. This is your Y bar. See, should be definitely bar. This is the empty model. See, this is the empty model. That if you need the regression model, how do you get the regression model? See, regression model is something we're going to go through that. That's a regression model. See, it's a regression model. See. So empty model is already within that one. Okay, empty model always over there. So if you say empty, they ask that if it is a empty model would be what? It is nothing but a horizontal line that shows the mean for minutes played. Mean for minutes played. Mean for minutes. So it is nothing but minutes mean. See, I write like that. See, mean of minutes means played. This one is what? Mean of free throw percentage. So this should be that answer should be what? Answer should be A. Okay, keep going. On the left in a salmon pink is a plot depicting this model, minutes IFT made and plus other stuff. On the right in royal blue is a plot depicting minute free throw percentage. It's a free throw made, other stuff. Which explanatory variable explain variation bit FT made or FT? Which explanatory we explain this one very well. Right. Look at for this one. For this one, almost like a see. What? I'm sorry. See, like a cluster. See, huge cluster. For this cluster, if you draw like a straight line, you can draw a straight line. That there are some outliers too. So this cluster, through this cluster, if you're trying to make something. If you're planning to use the straight line, it's kind of like a doesn't fit very well. But this one, look at this one. This one has an issue too. If you, excuse me, if you try to explain this one with like a straight line, that's another issue. That's why you're gonna go to the polynomial. See, I'm gonna get a curve like this. I'm sorry, curve like this. See, curve like that. Can I get a curve like that? Yes. So most of the time, this will explain very well by a polynomial distribution. This one is a cluster. Cluster will not be explained very well. See? That's what I'm trying to say that. See, this one and this one y means this one y also means, and this one x free throw made, this one x free throw percentage, PCT. Look at the heavy cluster here. Massive cluster, see, cluster like this. And here if you go to this one, look at. See, so this one, rather than straight line, you can use a curve. See, this one, can we use a straight line? It's not fair. So the huge cluster, see, it's a cluster. Cluster. We cannot even think of that any pattern that's going to go through that one. Unless otherwise we're going to use some heavy regression procedures, but that part we cannot talk about at this stage. See? But this one, at least you can set up with the word polynomial regression. What that means, you can think about y equals b naught plus b1 x plus b2 x squared. See, like a parabolic shape. Same variable, you're gonna square. See, intercept plus b1 times x. That means that you can see the slope with respect to this one, slope times ft made plus that slope square, some b2 ft made square. See, plus here, plus it. Or in R, how do you do this one? See, you can say poly model ln y. You can say means here and ft made plus ft made square. So this would be better, no? This would be better. Should be better. This one, I'm sorry, this one number 5. You can explain that one, okay? If you fit a model that predicts means by including ft made as an explanatory variable, how many parameters would the model have? See? That's it. You have how many? 2 parameters. What is the parameter? Y-intercept and the slope. Y-intercept and the slope. You saw that one. See? Those are the parameters. Parameters means y-intercept and slope. See? Y-intercept and slope. See? Y-intercept and slope. So this y means this x means that ft made, let's say that you have a straight line that to think about that going through cluster or that particular or that like this. Okay, my convenience, I'm gonna say like this to make it more accurate, because in the previous case they were doing comparison and which one would be better, but here let's say that we have like this. So this equation you're gonna write, we know y, this equation is nothing but y hat b naught plus b1 x. See, so y you're gonna be nothing but b naught plus b1 x plus e, or y hat plus e. See, you can write the several ways. That's the equation. That's the equation part. You can add to that one estimated part. So these are they're gonna ask about that would model have that how many parameters. This is in sample version. This is in sample. See, this is in a sample version. See? But its corresponding population version is the one we carry that what. See, x would be ft made. See, y would be what? Minutes. So for given each of these, you have a distribution. You have a distribution. You have a distribution. See, their mean will be centered. Will be together and then combined by a line. See, this line, equation of the line. You can remember yesterday we did expected value of y equals beta naught plus beta 1x. As a model, you can write the model. The model. Okay, here the method model 2. See, model you can write y equals beta naught plus beta 1x plus epsilon. This part we're gonna call e of y plus epsilon. See, another way to write it. See, expected value. See, so these are the parameters actually. See, parameters. See, b naught and b1x, or they are estimated. B naught and b1x, or beta naught and beta 1x. So the bottom line, how many? What are the parameters, or what are the statistics? Y-intercept and slope. So if you keep going, see, we fit our model means predicted by FT made. See, let and be player. If you know player had a 0 free throws, how many minutes would you predict he plays? 0 minutes free throws. If you know player had a 0 free throws, see, he didn't make any of them. That is the intercept. No? That's the intercept, 1622.31. That's the definition of that one. When x equals 0, what's the y value? Call the intercept. See? Intercept. Intercept. In another way, see? This much. See? This much. See? When ft made 0, this one. That's your intercept. See? That's the intercept. See? And 0. ft made 0. How much? How many minutes they have played? See, how many minutes would you predicted he played? Predicted value 1600. So C. Okay, so keep going. We fit a model means predicted by FT made and call it FT made model. FT made model. This one, the output is below. We also fit means predicted by points score, and call it points model. From this best fitting parameter, can we tell which model explain more variation? See. Look at the minutes by FT made, minutes by points. Same data. Then see, by looking at this one, can we compare and contrast these two? Yes, yes, no, no. Mainly, no, we cannot. We cannot do the comparison between two models based on their slope and intercept. No. They are based on their equations. You can write the equation minutes versus point. You can write the equation minutes versus FT made. their equation. By looking at the equation of that estimated line, regression line, you cannot make. You need the ANOVA table. No, we cannot tell from the best fitting estimate how much variability has been explained by model. No. We cannot tell from the best fitting estimate or best fitting straight line how much variability has been explained by model. You really need their ANOVA table, separate ANOVA table. And by looking at their sum of squared regression, sum of squared errors, then you can explain that. Okay? No. See, you run the following R code. Minutes first points now. See, data and detail. When you do so, you get the following output. See, points model. Points model 1156.60. Same thing. Same thing. Which of the following equation represent the fitted model? This is B naught plus B1 X plus E. So that should be this equation with X, okay? B with X, D is 0.680, okay? Plus 1.06 times X plus E. Okay. Our points model of the outcome variable means can be represented as this way, right? LeBron James scored 2,111 points in the 2011 season. In this equation, what part represents the prediction the points dot model would make for minutes played by LeBron James? He said, see, he would make for this. We are looking for the prediction for the number of minutes he played by when he scored this much of this many points. See, 2,111 points. So that part is nothing but you're going to plug in into this one. That's the estimated part. See? Estimated, see, prediction part. So this part, whole thing. You get the 2,000. You're going to find the B naught value. By running regression, you're going to find the B1 value. You're going to go to that LeBron James, that number of how much points that he scored. That one you're going to plug in into this one. So you need this part. We found that the best fitting estimate and put them into the FT-made model of the outcome variable minutes. You put it back into this one. LeBron James played 3,063 minutes, scored 2,011 points, and made 750 free throws in 2011 season. What is the FT-made model's prediction for minutes played by LeBron James? So this is based on the FT-made model. That means how many free throws. We don't have to worry about the other thing. Scored 2,000 points and made 758 free throws. You have to be careful. You don't need unnecessary one. Make sure that which variable they're talking about for X. X is nothing but free throws made. See how many free throws? 758 gonna plug in into this one. See here. Not the played, how many minutes he played. That's this one. Why? How many scored 2,000 points? No, it's for the points model. It's not the FT model. So it is 1,662.31 plus 2.83 times 758. See, that's how you're going to find that from that particular model prediction for minutes played by LeBron James. He actually played this many minutes, but you can get a estimate too. Then you find the difference between these two called the error. See, this is the estimated value, predicted value. This is real value. If you get this one minus this whole thing will yield what? The error. Okay. We have quantified error from the FT-made dot model of minutes and the points model minute by using the supernova function. Which of the following are reasons to think that the points model is better than FT model? See, FT-made minute points. See? Empty model doesn't matter. Regardless of that one, empty model would have the same thing, okay? Because it is based on that the number of minutes they played. See, minutes versus points, minutes versus FT made. Since we are using the same Y, they both, see, this is the empty model for what? When you have a Y only, Y is nothing but minutes. This is the empty model. When you have Y, see, they both have the Y, but they are using different x variable. Doesn't matter, same y. Because of that, you're going to have that same sum of squared error, unexplained sum of squared error, and degrees of freedom, and mean squared error for the empty model for both cases. Okay. So FT-made models PRE is less than the points models PRE. FT-made model PRE is less than this one. See, you compare these two. You can compare and then figure out which model is the FT model, SS model is less than the points model, SS model. You can compare SSR, SS regression between these two. The points model SS error is less than FT model error. Yeah, you can compare the sum of squared errors. 3 of them can be. That means all of the above can be utilized in order to do the comparison and contrast. Okay. Why is the SS total the same value for FT-made model and the points model? I just talked about that. Both are based on the residual from the mean of the same outcome variable, which is means. See? Residual from the mean of the outcome variable from. So that's for the y. Y you can remember y would be both. In both cases, y would be the same. See, same y. So they were talking about same y. See, same y. So they see you had a y like this. There's no x. See here in the no x. Wow. No x variable. Here you in the beginning you have y means. See? See? This is your y bar. See? This being explained with two explanatory variables. Same y I'm gonna keep here means, but for this one, for one I'm gonna use what? I'm gonna use FT-made, free throw made. The other one, still y is what? Minutes. X would be what? Points. Okay. See? But for both of them, where are they generated from? Where they come from? It's the empty model for both of them. See? Both of them. This is the points model. One is points model, the other one is the name is points model. The other one is FT-made model. Made model. They both are sprung or generated from the same empty model. They are different, that's a different story. See, why same y being explained. For both of them, same y bar gonna go, same y bar. See? Means y bar. See, that's the reason. See, if you get this one, see, y bar would be the same. See, y bar is nothing but means y bar. Here y bar is nothing but same y bar. Means y bar. See, this is nothing but means y bar. Means bar. Sorry. See? That's why. So both are based on the residual from the mean of the same outcome variable. Okay. Which of the following is the correct interpretation of MS total, mean square total, 397, 230 in the supernova table, mean square total. This one, okay? This total. This is roughly the total number of points in the data frame. Here, no. This is roughly the total number of squared means based on the random. This is roughly the average squared residual from the mean. This is what sum of squared residual from the mean. Sum of squared residual from the mean. Which mean? Empty model. See? Total. See? From the mean. Which mean? Which mean is the mean of y bar. Y bar. Minutes. Minutes mean. Okay. So from that one. Okay. And this should be what? If you divide by this one, that means if you divide by degrees of freedom, any number becomes the average. So that is nothing but the average squared residual from the mean. Sum of squared residual means squared residual from the mean has been average. That's the average. Okay, so see. So which of the following is the correct interpretation? Which of the following correct interpretation for pre 0.69 in the supernova table? 65% of the sum of squared you carried from the empty model can be explained by adding points to the complex model. Adding points means like not the points. Points means like points, the variable called points. The variable called points by that one, this points, okay? This variable, not the points here. The points he made, it's variable points. By adding the points, see 65% of the sum of squared you carried from the empty model can be explained by adding points to that. Means 65% of that empty model. See this from this one, the model has explained this much. That percentage is called this one. So it should be B. Okay. Do these data demonstrate that when a player amasses more points, this causes the coaches and other decision makers to give them more time to play? Why or why not? See, minutes per point. Do these data demonstrate that when a player amasses more points, this causes the coaches and other decision makers to give them more time to play? See? Why or why not? You explain that one, okay? By looking at this one. See? See? Minutes and points. Are they correlated? Okay, that discussion you build up to demonstrate that when a player amasses more points, this causes the coaches and other decision makers to give them more time to play? Yes or no? Would this cause? That's not the only reason for them. There's a relationship between that sorry, now minutes, number of minutes they played versus that the points they have amassed. But would that cause? See, coaches and other decision makers to give them more time to play or not? Okay, you can explain. We use this code to calculate the correlation coefficient, Pearson's R for minutes and points. Code. What we have found, a measure of how tight the data points are around the regression line. Yes, how tightly they were. See, spread out around the regression line. See, this one. See how tightly these points are spread out around the regression line. Is a correlation coefficient. So one of them. The slope of the regression line between the standardized minutes and the points. Yeah, that's nothing but the slope of the regression line between the standardized minutes and the standard this one. The strength of the bivariate relationship. Yes, all these three are the definition of the correlation for all these three. If you were to calculate the sum of the residual from the empty model of means, what would it be? Sum of residual, okay, not the square. Sum of residual from the empty model is always, you know that one, see? The data points are, see? Above and below, they were correct. Equally distributed. This will balance that the data. That's why we're going to utilize the average. So in that sense, more than the sum of the residual from the empty model is nothing but 0. In addition to the NBA player data for the 2011 season, we also have a similar data from frame called the NBA player 2015. Now they are trying to compare, contrast different years. Okay? Minutes versus points. Okay. Which of these values will be the same if we create two models with this line of points model, points 11 model, minutes points, this one, this data set from this data set. The SS total for both this model will be the same. No, the SS total for both this model will be the same because no, the best fitting estimate, no, none of these values will be the same for sure. Because what? Two different data set. None of these. See? None of these gonna be the same. Sum of squared regression, sum of squared total, sum of squared model, mean, nothing's going to be the same. Okay, because the 2 different years, 2 different data. In addition to NP player data, we also have similar problem. But they say that's the same thing. Okay, based on this scatter plot, which season had a higher correlation between minutes played and points. See, minutes versus point, 2 years, 11 on this one. If you go ahead and look at which year would have the higher correlation, closely see, which are so tightly that around the regression line. See, if you draw a regression line here, they were spread as. See, look at most of the points are far away from the regression line. This one little bit getting closer. Okay? So see, if you draw a straight line, see, they were tightly the spread out around the regression line. So you can say 2011. Okay, let's compare 2 models. One that treats point as a quantitative variable to predict minutes, and the other that uses points to create a 24 group before using it to predict minutes. The supernova table below shows that the pre-4 points 24 group reduces the total variation in minutes by 77%, but the points made reduces it by 65%. Why isn't the point 24 model better than the points model of minutes? See, let's compare 2 models. Okay, one treats the point as a quantitative variable. See, points as a quantitative variable. Then you get this one. It's a quantitative versus quantitative. Now what they did was the other that uses the points to create the 24 groups. You can use in the entile. You can that create, yeah. I'm sorry. You are referring to which question? C is also true. In which question? I'm sorry. I passed and go. I didn't see this one. Can you tell me which question that you're talking about? Which one that? C. C is also true for which one? I think I didn't see that. I'm sorry. Hello? Can you type in that which one? I think you said that a little bit while ago. What is the question? One, two. Which one? Which one you say? C also true, isn't it? For which one? Which question you are referring to this one? Hello? So, can you tell me which question that you are referring to when they say that C is also true? Hello? Which one? Hello, Benjamin, which question that you are referring to? Because I didn't see this one. Hello. Okay, that's okay. I think. Okay. Sometimes you cannot hear or something like that's okay. Okay. Let's get back to where we were. Maybe, okay. So 2011, we were on number 19. Okay, number 19. Now we were talking about that. See, this one as a quantitative variable, points as a categorical variable. And then when we looking at this one, you saw that the pre being 64%, here 65%, here 77%. See, see, see. Pre for the points group reduces the total variation in minutes by 77%, but the points more 65%. Why isn't the 24 group better than the points model of minutes still? See, but that's not enough for you to make the conclusion. But if you go ahead and look at the F, degrees of freedom has played a vital role here. See, look at this. Even though this value had gone up, see, compared to this one. But if you compare the F value, which one has a C? So with respect to degrees of freedom, see, because you have added more variable, excuse me, when you add the 24 groups, you are adding how many indicator variables? You are adding 23 indicator variables. Once you add the 23 indicator variable, that creates a problem. See, look at your degrees of freedom from that one. 23 based on the number of regressive variables. Here what? Here only one. So what I'm trying to say that when you have points, see, let's say that in this one points model, see, okay. If you go to the points model, see, points model, how do you model this one? You're gonna say y, okay, y equals b0 plus b1x plus error. That means you can say minutes equals b0 plus b1 times x. X would be what? Points. Points plus error. See, like that. Look at, you have only an x1 variable. See, 1x. See, this one is a, see, this one is a regression model. Regression model. We call this one regression. The reason what? This one is a quantitative. This one also quantitative. See, cont versus cont. See, but if you go to the other model, see, then instead of that one taking like that, you went to what? It's called the points 24 groups. Points 24 group model. Okay. On that one, how do you write this one? Y b0 plus b1 x1 b2 x2 plus dot 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 b23 x23. So it has been divided into 24 parts. See, having each one has what? Either what? 0, 1, 0, 1. See, like that. Those are indicator variable. Look at degrees of freedom. Degrees of freedom for regression is what? Number of regressive variables, 23. Here, degrees of freedom of regression is what? 1. That will affect to the F. That's why you have to get the one with the, doesn't matter that the pre has gone up, but still you have to look into what? F value. You're going to pick the one with the higher F value. Okay. One with the higher F value. See? That's why they say this is better. But still better. See, why isn't the point for info model better than this one? Because the F ratio shows that the points model explain more variation for degrees of freedom than points this one. More variation per degrees of freedom. See? More variation of degrees of freedom is nothing but, see, see, this one. More variation for degrees of freedom. Explain, see, the ratio shows that the points model explain more variation per degrees of freedom. It's nothing but F, or you can simply say mean squared model. Mean squared model. See, this one has a higher mean squared model too. See, O F, see, higher F. Okay, so that's A. Okay, see, okay, let's keep going. Okay, okay. Then you go a little bit further down. Speed dating is a date frame with the 276 observation and 22 variable. Data come from a study of speed dating in which each participant participated in a 4-minute date with a member of the opposite sex. At the end of the day, they can rate at the other on various attributes. In this quiz, we will focus only on the rating that females gave to the males, females to males only, and only on a few of the variables. Thus, the variables below, except for 2 variables that indicate the race of each participant, are all females' rating of their male date, each on a 10-point scale. The variables. This is the rating of their male, this is the rating of females' rating of their male date, okay? Like if how much the female likes the male. Attractive, a female's rating of male's attractiveness. Intelligent, female's rating of male's intelligence. Fun, a female's rating of male as fun. Sincere, female's rating of male as sincere. Share, shared interest, female's rating of male as having shared interest. Partner, yes, female's estimated of chance the male wants to another date. Race, male's race, Asian, black, Caucasian, Latino, other. Race, female race, Asian, black, Caucasian, Latino. If you are interested in females rating on how much they like their male dates, like F, in particular, you would wonder if variation in like F is better explained by how attractive they think the male is, attractive F, or by how fun they think the male is. Which of these plots would best help you explore this question? Same like last time, quantitative versus quantitative. Okay, then you can think about what. See, what is the best plot for this one? Again, quantitative like F or like F versus attractive F. See, better like F. See, how much they like their male dates. See, females rating of how much they like their male rate. It's explained by attractive F or fun F. Doesn't matter either one. You use scatter plot. Okay. Same like a question that we had last time. Okay. We fit these two, like was outcome variable. The first used the attractive F as the explanatory variable, the second intelligent F. Based on the parameter estimate for the two models, can you tell which model explain more variation in like F? See, by looking at this one, you get the like F being explained by attractive F, intelligent F. By looking at these regression line, you cannot tell nothing. No, it's not possible like last time, not possible for parameter estimate how much variation has been explained by model. No. D. See, similar kind of questions. We fit the model in like F as outcome variable, that's Y variable. The first use the attractive S as the explanatory variable, the second intelligent F. Above, we show the analysis of variance table produced by Supernova for the two models. Which of the following would make you think that the attractive F model explain more variation like F than the intelligent F model? Pre-SS model, SS error, everything you can utilize. Attractive model is greater than intelligent. SS model for this one. See, by looking at SS model, compare and contrast it with these two. O pre-value, O SS error. That means all the above. See, we made this plot to explore whether variation is being liked like F. See, might be explained by being perceived as F funnel. If we fit the empty model to this data, how would we depict it on this plot? See, it's nothing but a horizontal. See, their ratings go like this, and it's a horizontal line drawn the mean of like F. See, mean to the like F, like the same A. Okay. We would wonder if female likes male of the same race as 10, more than males of a different race. To investigate this question, we create a new variable called the race match with this code. Speed date in the race match, speed date in race. See, go to the data, race sim equals to female race to the male race. We're going to call that one race match. That race match will be utilized in order to explain the like F. We will then fit a model of like F using the race match as the explanatory variable. X variable is Y variable. How would you represent this race match model in GLM notation? Race match. Race is Y, V0, V1. Sorry, race match. I'm sorry. The like F is Y, V0, V1, and race match plus 0. See B. Okay. Then if you go to this one, we fit two models in which like F as outcome variable. The first use the attractive F as the explanatory variable, the second intelligent. Above we show that the analysis of variance table produced by supernova of these two. Why is the SS model have the same value for the two models? SS total, see? So you are using the same Y variable, like F, same. See? Can remember both are based on residual from the mean of the same outcome variable, same F, same Y. Sorry, same Y. See? Same Y. We had a similar question earlier too. See? So both are based on residual from the mean of the same outcome variable. Okay. See, above we saw that favorite set for the female rating of their dates, intelligent. If the researcher collected a new sample, 273 speed dates, what value in this output would be different? How the new data would be affect to that already existing data? Would that gonna affect to standard deviation? Yes. Mean? Yes. Median? Yes. Most likely all the above. It's gonna affect to the all the above if they gonna select that new data, 273 data. See, question is D. Then you have to run this one on this sandbox. Okay. Using the speed dating data frame, fit a model in which like is the outcome variable and fun is the explanatory variable. Based on the model, where would you predict a male's like F rating would be if his fun F rating was 0? When something is 0, see fun F 0, that's your X value, and the Y value is what? Like F. See? See? It's like this. See? So when you have let's say number 8 again, see? This one X, this one see? X would be what, Y would be what, Y variable would be like F. See? Then this one would be fun F. See? The central variable. What would you predict the men's like F rating would be if his fun rating? See? You're gonna fit in this one into regression line. This is the B naught. B naught is what? When fun F equals 0. That is B naught value. When fun F equal rating of 0, the value of like F is called the B naught. So you should get the B naught value by running this one. Then B naught should be, when you run, you can get that one 2.6. See. Keep going. Which of the following would be correct interpretation of number? This one. 3 points. This one. See. We talk about that one. Mean squared total. Supernova. Mean is nothing but roughly total number of squared means based on the empty model. See? Average squared residual. Squared means no. It's average squared residual from the grand mean. The average squared residual from the grand mean. See. Okay. Average squared residuals from the grand mean. This one is squared residual from the grand mean. Once it's been divided by degrees of freedom, it becomes the mean. It's a mean or average squared residual from the grand mean. Average from the grand mean. Average is coming because of 271. This part. So you have this many that data points over there. There's data points. If you get that one, this is for the all the data points. But if you wanna see get this done for per 271 data point, divide by on average you have this much of the residual from the grand. See, so that means this is actually what's gonna happen here. Then let's say that this one, what model to what model? Let's say that you have a light F to intelligent. Okay, doesn't matter any variable. So you have step number 9. Yeah. So you have, see, like this. Okay. So in the beginning, you have Y like it. You have X intelligent. Yeah, using different X variable from time to time. Okay. But okay, like this. Okay. That's the regression line. Okay. In addition to that one, we have a empty model line too. Can you remember? You have an empty model line. That's the empty model line. See? That's why it's the see? That's the grand and see. So if you go ahead and get the point and get this distance, that distance is the residual, see, error or residual from the grand mean. Okay. When what are you gonna do? You're gonna get that value. That value you're gonna get that value is nothing but this one. Let's say y minus y bar. See, I'm gonna square that one and I'm gonna sum them up. I'm gonna call that a sum of squared total. Rather than talk about this one, because this has been for how many data points? 4 degrees of freedom, which is n minus 1, which is 271 point. 200, is that 279? 269. Let me see. 268. Yes, this is not right. This number. So it should be 269 because 1 plus 268. See? 834. Okay, let me check. 834.85. Yeah, that 151.41, 677.430. No, this one, 828. This number is not right. See, this value. 3148 should be 8. 828. This one not right either. 3.086. This one is okay. But here we have an issue. Let's say this one 151.41C. I'm gonna do this kind of adjustment. 41. Can I write? No, that table I cannot change. This one right, but anyhow, this is right. Okay, so we don't have to worry about that one. Anyhow, this is nothing but okay. It should be the correct one. Should be right here. When this one is 828 into 8.842. Okay. The other one is 269. Okay. Then rather than looking for the sum of square total per that degrees of freedom, how much would that be? That's called average. Mean square total is sum of square total divided by the degrees of freedom of total. So 828.842 divided by, okay, 269, okay. 269, okay. So let's see that 828.842 divided by 269, 3.081, yeah, 3.081. Should be like that, okay. Not the one that we see here. Should be 269. This should be the sum of these two, okay. They both are wrong. This is right. But anyhow, that means, it's roughly the average squared residual from the grand mean. Squared residual. Average squared residual from the grand mean. See? Squared residual from the grand mean. See? This is nothing but the squared residual. See? Sum of the squared residuals or errors from the grand mean. See? From the grand mean. This is nothing but average sum of square. Sum of the average. You don't have to say sum. Average squared. Sum already been taken into average now. Average squared residuals from the grand. Average. Sum you don't need. Sum has been absorbed into the mean. Average squared. Okay, squared. Squared residual from grand. See. Let's go to this one. See, you have a y hat, you have a y bar. Here's a point. This has been, see, this been flipped, okay? See, so you know it is the blue circle in the diagram ever represent the data points in the group model. See, group model, two group models. See? You had a y hat, you have a y bar, you have a point. Which distance would be this used to calculate the sum of squares error? Sum of squares error. It's my point. Y minus y hat. See? Sum of squared error calculated by y minus y hat. Sum of square regression calculated by y hat minus y bar. Which distance utilized in order to calculate sum of square to regression? This distance. Which distance utilized to calculate the sum of square total? This distance. Okay. So this is so you see, look at that. You see, I'm gonna say this y bar. This is y bar. See? I'm gonna say this one. See. This is y hat. Okay. Y hat. So then we get the points. See? The data points. See? The data. See? Then same data you can see. This distance. You have this distance. Or you have this distance. See? This distance, see? This distance we're gonna utilize what? Y minus y hat. If you get, see, and square and sum them up, that's called the sum of squared error. See? If you get this distance is y hat minus y bar square and then sum them up, we're gonna call that a sum of square regression. If you get this distance, see, sum of square total, which is y minus y bar square and then sum them up. See, this is A, this is B distance, C distance, A distance for regression, B distance for what? Sum of squared error. See, so like that. Okay. So which represents A. Okay. So now, but look at this one again. See, y bar here, y hat here, y here, y minus y hat. See, again. If the diagram ever represent the data points in a regression model, which distance would represent the reduction in error? Reduction in error. Reduction in error. See? Reduction in error. See? This is the empty model. Empty model have this much of error. I'm talking about this gap. See? Huge gap from the point to y bar in the empty model. But that being reduced by, see, your model. This is sum of square regression. That's the reduction in error. This one is what? Error left over from the model again. So in another way, see, this one, in this model, see, if you have a, see, this one, you have a this one, see, and this is your point, see. This is y hat, this is y bar. So from here to here, y minus y bar, see, from here to here, y hat minus y bar, from here to here, y minus y hat, see. So the reduction in error, this is nothing but reduction in error, reduction in error of the regression model compared to the empty model. Compared to empty model, error has been reduced. See, if you get this one, see, reduction in error, that one. See, from this one, if you get this one and then see, y minus y hat and square, sum of squared error. From this one, if you get y hat minus y bar and square, so sum of square regression. From this one, if you get this distance, I'm sorry, this distance y minus this one y minus, this is sum of square total. Sum of square total, okay, this one, right. If you get this one, y minus y bar squared, sum of square total. This one, y hat minus y bar squared, sum of square regression. Sum of square regression is responsible for the reduction in error. Okay, then our answer should be error is given by this distance, which is b. Okay, which is b. Okay. It's not hard. Okay, so pretty much that we done the quiz 2. And then if you have any question, just email me. I'm grading and then in the previous class, everything, and then wrapping up. And make sure that you're going to turn in all your assignments by Sunday. And for this class, that as the usual, that we don't have a strict deadlines for that assignment submission. But for the last class, all the assignments should come to me by midnight Sunday, because that I had to grade. I'm right now grading everything, and I had to finalize grades and send to that registrar office by around like noon Tuesday. So at least that I had to finalize everything on next Monday. So that's the end of the today's session. And then I'm gonna go ahead and then, since I have already recorded this one, anybody that missed that one, you can play this video. I'm gonna upload to our homepage, so you can go ahead and watch and then get a clear idea what's going on in the regression model. And then we keep discussing that one next week, chapter 9, 10, and 11, go like that, and then build up the more elaborative knowledge, okay, broad knowledge on regression. So I'm gonna let you guys go, and you guys have a great weekend, and then good night, and then see you guys on Monday. Take care. Bye bye. Thank you very much.